So now next speaker is Andreas Geiger. I think,
Hello.
hey, you can start sharing your screen. So for a brief introduction for Andreas, he's a professor at the Autonomous Vision Group at the University of Tübingen and MPI for Intelligent Systems. He's done a really amazing work on 3D scene understanding, reconstruction, motion estimation, especially including generative models. One of the best paper awards for no, not the only one best paper award for CPR 2021, which is Giraffe, um, is really outstanding work in this area. And he was also the recipient of the PAMI Young Researcher Award and many other awards at 3DV Best Paper Award, creator of the Kitty dataset. That's also really large impact in the community. Okay, so Andreas, you can take over and start your talk.
Great. Thanks a lot for the nice words and welcome everyone. Giraffe is what I'm going to talk about today, amongst others. I'm going to talk about generative neural scene representations for 3D-aware image synthesis. So maybe what was already alluded to in the previous talk, we are trying to go here in this talk more towards unsupervised 3D representations. And in particular, I'd like to talk about these three works here that are in line and build upon each other. The first that we did was called Graph, Generative Radiance Fields. The second, Giraffe, at the CVPR. And then very new, Campari, just accepted to 3DV. And these are my amazing collaborators. Michael Niemeyer, who did a lot of the work behind Giraffe. Katja Schwarz was the main author on Graph, and my former postdoc. Let's get started. As we all know, generative models are fantastic, no? So how do they work? In a nutshell, sample a latent code from the prior distribution. And then we have a nonlinear function, a generator G with some parameters theta, a neural network that takes that normally distributed latent code and then generates a more complex distribution, in this case an image distribution. This is an example from StyleGAN. It's really amazing what these models are able to do. This is a real example from StyleGAN 2. Here's another example from StyleGAN 2. And here is yet another example from StyleGAN 2. So we can sample more and more latent codes to get different generated images. But I want to pose this question here. Is generating photorealistic images all we need? Or do we desire something more? And I would argue that for many applications, we require control. In particular, we require control over many aspects of the image generation process. Think about animation movies. If you want to synthesize scenes like this with little human effort, then you need to be able to generate individual assets, but then control them in the scene. Or video games. Video games is another great example where you want to have full control. You want to control the environment, the state, and as the game engine, but then also you want to hand over some of this control to the player. So you need to be able to modify the image content. And of course, also virtual reality is another example for this. So what we are looking for, what we were after in this line of research, is to build a generative model that is 3D aware and that can do 3D aware image synthesis. And in particular, this model should allow us to do the following. It should allow us to generate photorealistic images, control individual objects with respect to intrinsic properties, for example, their appearance, pose, and size in 3D. These are 3D properties, not 2D properties. And then also control, of course, the camera viewpoint in 3D. And what is making this problem really hard is, as we phrase it, is that we want to train this from unstructured and unposed image collections. So we want to use as little prior knowledge as possible, just a collection of images from a specific object category, for example. The first question that we have to answer here is, what representation should we use for 3D-aware image synthesis? So in the past, different representations have been tried. For example, Platonic GAN uses a voxel-based 3D shape representation and a volume rendering step here. So latent code generates a 3D object in terms of a volumetric voxel-based representation that's then rendered into an image. The advantage of doing that is that it's multi-view consistent by design. You generate a 3D object and you render that 3D object. So whatever you generate, it will look consistent across the different viewpoints. But this approach, at least this early approach, doesn't lead to very high image fidelity. As you can see here, this is the image that has been generated from this approach and has relatively high memory consumption because voxels don't scale so well. Another approach called HoloGAN uses a voxel-based 3D latent feature representation with a learnable projection. The idea here is to sample the latent code and to generate a feature volume, and then to render that feature volume with a neural renderer into an RGB image. Now this allows for higher image fidelity, as you can see here, but the object shape and identity now vary with the viewpoint due to this learnable projection, because this learnable projection in a sense makes this 3D consistent representation 3D inconsistent again. So if you render from different viewpoints, the object identity or shape might change. And if you try to reconstruct then, for example, using a call map, you don't get a very nice reconstruction from that. So what we proposed in, this was in NeurIPS 2020, is Graph, a model called Graph, Generative Radiance Fields. And the idea here is to build upon NeRF, the NeRF representation, the neural radiance field representation that takes a viewing direction and a location as input and maps that to color and a density value, and uses a non-trainable volumetric rendering step to render an image, to use that representation in a generative setting, in a GAN setting, where we sample a latent code, we condition on that latent code, and then we render an image based on this conditioning. And this is an example of our graph method. And you can see that because we have no parameters here in this rendering step, that we obtain a consistent 3D reconstruction if we take these images, a couple of images from different viewpoints rendered from this model, and try to reconstruct that again. So we have a continuous representation that's multi-view consistent, leads to relatively high image fidelity, at least on these very simple data sets that we applied it to. It doesn't yet work on very complex scenes, but on this kind of data set it works. And has low memory consumption because we're using this very compact radiance, neural radiance representation where this mapping is represented through a neural network. So let's look at this model in a little bit more detail. What we do first is we sample the camera matrix. These are the camera intrinsics, the camera pose. These are the camera these are the camera intrinsics. These are the camera extrinsics, and a patch sampling pattern. A pattern along which we want to compute the appearance. We do this because it's intractable to render entire images with this NeRF representation, as this is very time and memory. It takes a lot of time and memory. So we just render a patch that we sample randomly from the virtual camera. And then we have a patch generator and a patch discriminator, similar to a patch GAN. So here's an example. This is from this virtual camera where we sample this, in this case, 5x5 patch pattern in a 5x5 pixel pattern. In reality, what we do is we have a 32x32 pattern. So then we pass these parameters to the generator, which samples the corresponding pixels and rays. And then for each of the pixels, or a pixel and a ray is the same thing here, right? So for each of these pixels or rays, we can sample 3D points along the ray, as in the neural radiance field approach, which we need for volumetric rendering the image. So we sample the space along these rays. And then we pass this through through a positional encoding, the view direction and the 3D point, and use it as an input to what we call the conditional radiance field. And this is a conditional radiance field because it's also conditioned on a latent shape and appearance code, illustrated here, that are sampled from latent low-dimensional Gaussian distributions. So we condition on the shape and appearance as well. And the output of this conditional radiance field is then the color and the density for each of these points along each of these rays in the pattern. And then we apply volume rendering, which is basically just doing alpha composition on these points in order to render the pixel colors for this particular patch that we have sampled. And this is what we call the predicted patch P dash. Now we want to compare this patch to real patches. So what we do is we take real images and we sample real patches using the same patch sampling procedure, that we get a patch of the same size, also 5x5 or in practice 32x32. And because now we have a very standardized patch size, we can use a very shallow and standard 2D confident discriminator to compare these two with respect to each other. And of course, what we do in practice is we sample these patches randomly. So we sample the dilation factor here randomly. We sample also the location and the scale randomly, so that all areas of all regions in the 3D space and all areas of the image are eventually covered over time, stochastically. Okay, so yeah, the key idea to summarize is that we have a generator and a discriminator for image patches. The generator has a non-trainable deterministic volume rendering component, but a trainable conditional radiance field. And these patches are sampled at random locations and with random scales using random dilations. Let's have a brief look into the architecture. So this is this little orange block that we are looking inside now, this conditional radiance field. We have a fully connected MLP similar to Nerve, where we input first the 3D location and the shape code. So at the very beginning, we insert the shape code, but the appearance code CA and the view direction D influence only the output color. So here we're encoding this into a latent code H, and then we are branching out to a density head and then to a color head. And only the color head is influenced by the viewing direction and the appearance code. And this allows us, this inductive bias allows us basically to disentangle the shape and the appearance. So we have multiple inductive biases in the model. One inductive bias is this here. The other inductive bias is, of course, that we force the entire image generation process to go through 3D space. These are the main two biases that we are using here. So let's look at some results. These are some results of Graph on the synthetic Kala generated cars data set. But again, this data is generated without providing to the method any information about the depth or the viewpoint. What the method sees is only a random collection of images, of rendered images. And as you can see, it can then synthesize novel cars with novel shapes and appearances decently well on this simple data set. We can modify also the shape and the appearance. And we also get automatically the geometry here rendered as a false color-coded depth map, despite the input to this method is only RGB images. Here's another example, and this is on real data on the Celeb A dataset at also 256 times 256 pixel resolution. And again, here we get the corresponding depth map out of our learned model. The next thing we wondered is, well, how can we scale this idea to more complex multi-object scenes? And this is where we started working on Giraffe, which is this CVPR 21 paper. In Graph, we incorporate a 3D representation as an inductive bias into the generative model, as we have seen. What we do now in Giraffe is that we incorporate a compositional 3D scene representation into the generative model. The difference is that now we have a compositional model. And again, we want to train this in an unsupervised fashion from an unstructured, unposed image data set. So the data set doesn't change, only the model changes. And what we do in addition is we incorporate a neural renderer to yield fast and high quality inference, which means we are giving a little bit up on 3D consistency here now. We have a trainable rendering part, but the advantage is that we can train much, much faster this model and get better results, at least in terms of FID scores. So let's walk us through this model. The first thing we do is we sample n shape and appearance codes, where n means the number of objects in the scene and the background. So n is the number of objects plus the background. And also we sample this randomly. So depending on how many objects we expect, but over a random set. And then we, for each of these objects or the background here at the bottom, we obtain we generate a so-called feature field. In contrast to Graph, we don't directly generate with our multi-layer perceptron the color value, but we generate a higher dimensional feature representation continuously in 3D space. And the advantage of this is that when we render this, we can render this to smaller resolution, and the rendering is the slow part, so we can have faster rendering. And then we have a 2D still a 2D convolutional rendering step that upscales this feature map then to a higher resolution image. As a note here, what we show is RGB colors. So this might be a bit confusing, but it's just easier to visualize the colors rather than the features. So what you see here is colors, but what you need to think is features. So these are the sampled feature fields. Then we sample also the size and the pose of each of these feature fields. So you can see this little bounding box. So we have a local coordinate system, and we sample the pose and the size of each of those to stage them in the scene, indicated here by this little square at the bottom. So we have the background staged, and we have all the objects in the scene staged now. And then we composite them together. We composite all feature fields into a single 3D scene representation, and then sample a camera pose. Let's say this is our sampled camera pose. And then we perform volume rendering in order to get a low resolution feature image. And then we have this bespoken 2D decoder that upsamples this feature image. Here we are still in the feature space, not in the RGB space. But then we upsample this and output the final RGB color image. And at test time, we can then sample individual codes. So illustrated here, we can draw random samples from these distributions to control the shape, appearance, and pose of each of the objects and the background. Just to highlight again, the key here is that we volume render the feature image at a smaller resolution and then upsample via the decoder to make this tractable and fast. Unlike Graph, we can then directly train with an adversarial loss at full resolution. So we don't need a patch-based discriminator anymore, but we can directly train with the full resolution images. This is the architecture of Giraffe. It's of the conditional part. This is almost the same as Graph. The only thing that has changed is the feature head, right? So before we had a color head, now we have a feature head. We're outputting not free values here, but a higher dimensional feature vector. That's everything that has changed inside this conditional radiance field. And then the scene composition is rather simple. Just to go back, so we need to composite these objects together, right? So how do we do that? Well, we have n feature fields that each produce a density and a value and a feature vector. And then we combine the densities simply by summation and the features by density weighted averaging. So we just compute a weighted average and sum the densities of the individual objects in order to obtain the final density. Okay, so this is everything about the method. Let's look at some results. The first result is a comparison in terms of object translation for a 2D based GAN and our approach on the right. As you can see here on the left, the 2D GAN is not able to disentangle translation or position and appearance entirely. As you translate objects, for example here, the shape and the size and also the appearance of the object often changes. So it's just hard to do this without this inductive bias of going explicitly through 3D and disentangle the objects into different objects, disentangle the scene into different objects. On the right, however, you can see that we can individually now stage the scene because we have individual object representations available. And so they are consistent. We can also do more complex operations like circular translations, as shown here, which is impossible. So we can't get that level of control with a traditional GAN. We can also add more objects at test time than we had available during training time. This is an example where we trained on 2 object scenes, but then at test time we staged the scene with more objects in it. And we can also rotate the object. Here's an example on a car data set. You can see that it's a little bit overfitting to the canonical poses because the data set is very biased. It has a lot of observations from front and back and side, but less from intermediate angles. And we can translate the object. And we can change the object shape. So here on the left, the shape of the car, on the right, the shape of churches in this example. And we can change the object appearance. We can even generate out of distribution samples. So what you see here is samples where the car is translated more than it was translated in the original data set. Or we can add additional cars into the scene, that more cars than were present in the original data set. Here's a little comparison of the rendering time to illustrate, highlight the difference between this low resolution feature rendering and then upsampling compared to directly rendering the RGB image with a neural radiance field representation. You can see that it has a big impact, in particular if you go to larger resolutions, you get a quite significant speed up with that. Now, finally, the last project I want to briefly show to you is how can we extend this to learning also the camera distribution. What I didn't tell you so far is that in Graph and Giraffe and all the works that appeared at the same time with a similar goal required very careful tuning of the camera pose distributions. So given the data set, you first looked at the data set and then you were trying to figure out what is a reasonable distance of the camera and focal length, and what is a reasonable elevation angle of the camera, and then you picked some distributions that capture that precisely, because if you don't do that, the generation will just break. It will not learn anything meaningful anymore. So what we tried to do in this project is to lift this restriction by learning a 3D-aware image generator and a camera generator jointly. And it turns out that this actually works. So what we do now is we sample a prior camera from a very generic uniform prior distribution where this camera is parameterized through its intrinsics. We use the focal length in X and Y direction and the extrinsics. We assume the camera is on a sphere at a certain distance to the center, is looking at the center, and at a certain elevation and azimuth angle. So we start with a uniform distribution over all of these. We sample this Xi prior from this uniform distribution. And then we have a camera generator. This is again a nonlinear function implemented as a neural network that maps this quite uniform distribution to a nonlinear multimodal distribution, Xi prediction. And then we feed this into the 3D-aware image generator. In this case, we have a model that treats foreground and background separately, but we don't model more than one object, more than one foreground object in this case. And then we have a standard discriminator, a standard adversarial objective similar to Graph and Giraffe. So here I want to show you some results. What you see here is a histogram or distribution plot over the elevation angle on the x-axis. This is one of the camera parameters now, a one-dimensional space illustrated here. And we can see that starting from a relatively uniform prior here in blue, the model now, including this step of also learning the camera distributions, learns that in this particular data set, here in green, the distribution has actually 4 modes. So there's 4 elevation angles that are more likely than the others. Or here's another example where we start from a uniform distribution and then learn to approximate these 2 modes of this different data set. And this has quite some impact on the results. If we compare these non-tuned generative models, and here are some samples drawn from trained but non-tuned standard generative models like Graph and Giraffe, you can see that it's not consistent, it's not leading even to very nice photorealistic results. And when you rotate, this is the rotation axis, when you rotate, sometimes rotation doesn't even happen, sometimes rotation changes the shape or the appearance, so it doesn't really work. But if we also learn jointly now the camera distribution, we can get nice results again, similar to the results obtained with hand-defined parameter sets. This concludes my talk. I want to briefly summarize. We proposed novel methods for 3D controllable image synthesis. We demonstrated training from raw unposed image collections and incorporated compositional 3D scene structure into the generative model as inductive biases. And this allowed us to gain explicit control over individual objects during synthesis. In future research, I think we should address scaling to larger and more complex multi-object scenes, and also to enhance photorealism to match 2D guns like StyleGun 2, for example, which we don't match quite yet. Also, disentangling lighting, materials, etc. is an interesting direction for future research, I believe. With that, I want to close. Thank you very much for your attention, and I'm looking forward to any questions that you might have.
Thank you very much. It's really exciting work that you have presented. I think Chris has a question.
Yes, while people are typing their questions in the chat, I can fill in a quick question that basically concerns the last part. Going from learning the camera pose distribution, you could also think about learning the object pose distribution, or where objects are in the scenes, how many they are, and so on. Have you thought about that? I guess the difficulty there could be that these models like to cheat and might collapse into a mode where it just reconstructs part of the data set.
Yes, indeed it becomes quite hard. I mean, you're right. In the sense there's this duality, right? Well, focal length, you need the intrinsic, I guess you need to model really in terms of the camera parameters. But what effectively what we did here in this in the case of Giraffe, let me go back. Was to assume the background to be fixed and instead model the camera with respect to the background, because of course the pose distributions of the individual objects are modeled. Yeah, so I guess the question is in which parameter space do you want to model this? I think you could also model it in the backgrounds, like you could model the pose parameters completely here in the background, except for the intrinsics probably. But it becomes harder because then you have to disentangle these. I mean, then you have all the compositionality of the backgrounds with respect to the objects, right? So that's why we choose this kind of spherical representation for the camera. But it's a good question. I don't have a very good answer to that. Yeah.
Great. We also have a few questions from the audience. So the first question is, like, if you need to interpret a given image or video, would these models be useful?
I think so. I hope so. We don't, I mean, we didn't tackle this, but of course you could run like GAN inversion techniques and try to, or train an encoder jointly and try to infer the objects from a single image and then manipulate them. I think, for example, where this could be useful is if you can do it photorealistically, is to generate more training data by manipulating objects in a scene photorealistically. Or one thing that we are currently looking a bit into is differentiable and trainable differentiable and trainable simulators, where in the end you could even place a little sensory motor agent that does something in that environment and basically interacts with that environment. So I think it would be very useful to have that, but we are also not at the photorealism. We haven't achieved the photorealism that we'd like to achieve. So, but I think it's certainly possible to implement encoders or inversion techniques that figure out the latent codes for these scenes.
I think the next question connects like really nicely to the question, this question, which is what is the motivation behind adversarial training in these models, besides like when we don't have these labels, when the data is unlabeled, is there any other like motivation for using GANs, adversarial training?
Well, in our case, we couldn't use anything else. In comparison to a VAE, for example. I mean, in our case, we have unstructured image collection, so we don't have paired examples, right? So, but of course, we could try to do this with a VAE, and I think there's a paper from DeepMind that does something like this with a VAE. In the past, we have always struggled to get the same fidelity with VAEs as we could get with GANs. So I don't think it's a fundamental limitation, but it's definitely not easy to reach the same level of fidelity. And that's why we use, at least if you use VAE-like models, typically you have to combine them with adversaries to get photorealism. We haven't explored that more, but at least our initial attempts weren't very successful, I have to say.
Okay, and there was also another question, which is, can we replace the NeRF representation with more surface-based representations like occupancy fields or volumetric and like Uniserve?
Yeah, sure. Why not? I think the main problem or the main difference or the main reason why we choose these type of representations here is that they allow you to train from scratch. So if you look at like surface representations, they typically require some input masks to start from. Unless, like recently we have tried to lift that a little bit, that's true with Uniserve. So we have kind of a hybrid between the two. But the reason is that without masks, these models will just break because they are, like for the background, they can't reconstruct them very well. And so they also mess up the foreground because they can't capture the entire scene. Whereas in radiance field, like volumetric representations, you can represent all the fuzziness and start with a really fuzzy initialization, if you will, and then converge to, at least in the areas where you have enough information, converge to something reasonable. But I believe that they can be combined, right? So but it's hard to start directly with a surface representation, I would say, in particular for the background, because the surface representation always has to commit. It has to commit to a surface, right? If you don't know something very well, then it's bad to make a commitment in a sense, right? So I think you would need to bootstrap also or combine this somehow.
I also have a quick follow-up question on this. Like, is there any way to deploy some explicit controls over these like implicit representations? For example, if you want to like edit part of the scene using a NeRF, like how would you do that?
Well, I mean, here we try to do that by decomposition into individual objects. But if you ask, how would you manipulate individual elements of an object, like the front light or something, where you have modeled them already at the object level. I mean, that is not covered by our approach. So either you model more fine-grained, yeah, you have a deeper hierarchy in a sense, but then it becomes also harder to train. I think then you would need to start using some supervision probably. Or there is some nice works that recently have shown that actually there's nice semantic embeddings also encoded in unsupervised trained radiance field representations, and you can then build on these semantic embeddings. I think that would also work, right? So if we want to change the color of the car or something, or the color of a certain area of the car, I think something like this could work.
Great. Thank you very much. I think there are a few more questions on the chat. If you have time, you can look at them, and
Sure.
We'll probably move on to the next talk.
Thanks for having me. Yeah.
Thanks.